And welcome back, guys. Today we're going to be taking a look at topic 7.5, which is on absolute value equations. Now, this is the last topic in this unit, so we're going to be using a lot of pieces that we learned previously in this unit as well. So today we're looking at solving absolute value equations. And so up to this point, we've been working with absolute value functions, which would be written as y equals f of x. And now we're going to be solving equations. And if you remember from previous units, that means that we're going to have something set equal to 0. And so when we have an absolute value function, it's y equals, and when it's an absolute value equation, it's 0 equals. So now we're actually trying to solve for x. And so the solutions of that equation are also known as the roots of the equation. And if it's a function, we call them the zeros of the function. So the solutions or the roots are also the x-intercepts or the zeros when we're graphing the function. Now, some things to keep in mind. When we're solving for absolute value functions, we're going to have to consider two cases. And so for here, if a is greater than or equal to 0, if we have absolute x is equal to a, then x could be positive or negative a. For example, if we have absolute value x is equal to 4, that means x is either a positive 4 or a negative 4. Now, when we're trying to solve graphically, we can graph the equation y equals absolute value of x. Let's say we're trying to solve y equals absolute value of x is equal to 4. We can graph the function y equals absolute value of x, and we could graph y equals 4 and find out where those 2 points intersect. So if we're solving graphically, we can do it this way. Another way to do it, and we're going to look at these in the examples, is to rearrange your equation and have the absolute value of x minus 4, graph that, and find our zeros. All right, so let's take a look at some examples here. Now, first of all, if we want to solve absolute value equations, we have to consider both cases. So in all of these, we're going to consider a case 1 and a case 2. For case 1, we're considering that the domain is greater than or equal to 0. So in other words, x is positive. And the second one, we're looking at the solution having the domain being less than 0. In other words, we have to look at the case where x is negative. So we'll start off simple here. We've got absolute value of x is equal to 3, and we have to solve algebraically. So if we were to actually graph this function, we could graph the absolute value of x, and we could graph y equals 3, and we're essentially looking for where those 2 points intersect. And so case 1 would be a positive x, and so we're basically talking about what's inside that absolute value has to be positive. So if we have a positive x set equal to 3, that means x equals 3. Now, if we have case 2, this is where we're looking at the part inside the absolute values being negative. And so in this case, we just have the x. So a negative x is equal to 3. That means x is equal to negative 3. Now, we can always double check to see that that works. If I were to substitute in absolute value of 3, I get 3. If I sub in absolute value of negative 3, I get negative 3. So that would mean my points are intersecting here when x is 3 and when x is negative 3. All right, so let's get a little bit more complex here. The next one we're going to look at here, we have absolute value of 3x plus 2 is equal to 4x plus 5. So again, we're going to consider our two cases. Case 1, we have a positive 3x plus 2. And case 2, we have a negative 3x plus 2. Notice that I have the 3x plus 2 in brackets. So case 1, we have a positive 3x plus 2. So 3x plus 2 is equal to 4x plus 5. Rearranging, I'm going to have 3x equals 4x plus 3. So if you've noticed, I've subtracted 2 from both sides. And then if I subtract 4x from both sides, I'm going to have negative x equals to 3 and x equals negative 3. Now for case 2, I have to consider the negative scenario. So I'm going to have a negative 3x plus 2 is equal to 4x plus 5. Bringing that negative through the brackets, I'm going to have negative 3x minus 2 is equal to 4x plus 5. Now, rearranging here, I can do this in one step or two steps if I choose. I'm going to add 2 to both sides. And at the same time, I'm going to subtract 4x from both sides. And so what that's going to give me is negative 3x minus 4x is negative 7x. and a 5 plus 2 is 7. Now when I divide by negative 7 on both sides, I'm going to have x equals to negative 1. Now, if you take a look at the bottom of your page here, it says each case creates derived equations. So when we're dealing with these equations or we're dealing with these cases, these are derived equations. And so they may not always be true. And we know from working with other units where we were working with radicals or we were working with rationals, we had to check for extraneous roots. We have to do the same in this unit. The roots of the derived equations have to be verified. So we're going to do our left side, right side verifications for both of these to check for extraneous roots. So in other words, what we always have to do, we always have to check for extraneous roots. Now again, because we do that in other units in this course, this is not anything new. So we're always checking for extraneous roots. So first one here, we're looking at doing a left side, right side verification. And when we're subbing in using the original equation with the absolute value symbols. So here we have x is negative 3, so it's going to be 3 times negative 3 plus 2, all in the absolute value symbols. That gives me negative 9 plus 2. Absolute value is negative 7, and that is 7. Now on the other side, we had 4x plus 5. So we're going to go 4 times negative 3. Notice there's no absolute value symbols on this side, so we don't need to worry about that. Negative 12 plus 5 is negative 7. Well, a positive 7 and a negative 7 are not equal. That means that x equals negative 3 is actually extraneous. So then we're going to check the other equation. Again, LSRS. And on one side, we have the absolute value of 3 times negative 1 plus 2. On the other side, we have 4 times negative 1 plus 5. And so I have negative 3 plus 2 becomes negative 1. And when we take the absolute value, we get 1. On this side here, we have 4 times negative 1 is negative 4, plus 5 is positive 1. This one works. So for this particular question, we only have one solution. X equals negative 1. All right, now taking a look at the next piece here, we're going to look at how to solve graphically. Now we talked about that a little bit in the notes, but now we're going to go through some examples. So when we're solving graphically, there are two different ways that we can go about doing this. One is to graph each equation separately, y1 and y2, and intersect them. The other one is to manipulate the equation, move everything to one side, and set it equal to 0. So the first method here, I have absolute value of 2x minus 5 is equal to 5 minus 3x. We're going to make the first equation y1, and we're going to make the second equation y2. Now, when we graph that on our calculators, we're going to have something that looks like this. And then we're going to have another equation that comes down here. And our intersection point would be right here. Now we're going to check this on our calculator just so you can see what it looks like graphically. But when I intersect these are going to intersect at 0, 5. And if that's where they intersect, that means x equals 0. So let's take a look at that one on our calculator. We're going to graph math over to number, choose absolute, and we've got 2x minus 5. And then for our next equation, we have 5 minus 3x. Now when we graph those, we're going to have that nice V shape and our line, and we're going to find the intersection point. So we have second calc 5, enter, 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 and we have an intersection at 0, 5. So again, our answer is 0. Minus 5 is equal to 5 minus 3x. We're going to manipulate this equation and move everything to one side. So what that will give us is absolute value of 2x minus 5 plus 3x equals 0. Now remember, when we're moving things across the equation, as we switch sides, we switch signs. So graphing this on our calculator, this will look like a graph you probably have not seen before. We've got our absolute value of 2x minus 5, that's already punched in, and then we're going to subtract 5 and add 3x. And taking a look at that graph, we have something that looks like this. Now, once we have that graph, what we need to do is find where it crosses the x-axis, so where our zeros are. And so we can do that one of two ways. One is to do second calc, choose number 2 for 0, and then we're going to go on the left-hand side of the intersection point or intercept, and on the right-hand side, hit enter, enter, and we have 0, 0. The other way to find our x-intercepts is to draw a line at y equals 0. Again, you won't see the line there because it's right on the axis, but we can do our intersection. So second calc 5, enter, 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 and again, it intersects at 0. So sketching a graph here, I'm not so worried about the graph being exactly accurate in terms of scale, but definitely want to make sure that we go through 0, and then you show that the graph shoots off. So right here, we have an x-intercept at 0, 0. That would mean that x equals 0. Now moving on to another example here at the quadratic equation, we're again going to try to solve graphically. If I were to graph this one on my calculator, I'm going to start off with method 1. I would graph 2x squared plus 7x minus 1 all in absolute values. That would be y1. And then I draw a line at y equals 3 as y2. So taking a look at our calculator, we're going to go math over to number. And we've got 2x squared plus 7x minus 1. And then we can draw a line at 3. And so we have our function there, and then we can find all of our intersection points. Now, if you notice, we have 4 intersection points. So I want to start on the leftmost one here. So if I take a look, that's at about 1, 2, 3, 4, maybe a little bit past or just a little bit before -4. So if I trace at -4 or -5 on my calculator, that's actually going to get me close to that point. If you wanted to trace at -4, probably gets you a little bit closer. So right there. And so once the cursor is close to that point, then it's easier to make sure that's the intersection I'm going to deal with first. So second calc 5, enter, enter, enter. And our first intersection points happened at -4. Then we're going to do our next intersection point, second calc 5. Just make sure we're just a little below it. Enter, enter, enter. We've got -3.2. Second calc 5, move on to the next one. Enter, enter, enter. And -0.32, and then one more. So second calc 5, again, make sure we're closest to that point. Enter, enter, enter. And we've got 0.5. Now you don't have to be necessarily below the point, you just have to be closest to that intersection point for the calculator to assume that's the one that you want, or to know that that's the one you want. We'll do a quick sketch of our function here. So we go down, up and down, and we know that we have these 4 intersection points. We intersect here, 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 and here. Now, based on what we found on the calculator, our intersections happen at the following points. So we have one at -4, 3, -3.2, 3, -0.3, 3, and at 0.5, 3. So that means that our x values are -4, -3.2, -0.3, and 0.4. So that would mean that we have 4 different x values that would make that statement a true statement. Now, if you choose to do the other method, if we wanted to graph this as absolute value of 2x squared plus 7x minus 1, all in absolutes, minus 3 equals 0, we can do that as well. Now, taking a look at that graph, here would be our function. So we've got y equals, we're going to subtract 3, we're going to turn this into a 0, or you could just leave it blank and then do your 0, and then we have this as our function. Now again, we can do this by checking out our zeros. So we can go second calc 2 for 0, and we can go on the left-hand side, arrow down, enter. We have -4. Then we can go to the next one, second calc 2 for 0, enter. and you'll be finding that we're getting the exact same values. So doing it using this method, we would also have -4, -3.2, -0.3, and zero point 0.5. So ultimately, it doesn't matter which method you choose, as long as you're getting the correct answers. So -4, -3.2, -0.3, and 0.4. Here, we would have our graph come down, up, down, up, and we would have our 4 points here at -4, -3.2, -0.3, and zero point 0.5. Again, I'm not too worried about scale so much as just making sure we've got a quick visual of what that graph might look like. All right, let's take a look at another example here. We're going to solve this one algebraically, and then we're going to verify graphically with our calculators. Now we have to consider both cases. So again, absolute values, we're always having to consider both cases. First case here is positive. So we're going to have x squared minus 2x plus 2 is equal to 3x minus 4. We're going to rearrange our equation. So we're going to move everything to the left-hand side. X squared minus 5x plus 6 equals 0. And I'm going to factor. So the reason I was pulling everything to one side is because I saw that there was an x squared there. That was a trigger for me to know that I'm going to have to factor. So again, I was looking for two numbers that multiply to be 6 and add to be -5. So I've got -3 and -2. Solving those, we have x equals 3 and x equals 2. And again, we're going to double check for extraneous roots, but we're going to do that at the very end when we solve graphically. So case number two, we have to consider when that expression inside the absolute value function is negative. So a negative bracket x squared minus 2x plus 2 is equal to 3x minus 4. And when I'm multiplying through, I'm going to have negative x squared plus 2x minus 2 equals 3x minus 4. I can again move everything to one side, and I'm going to have x squared plus x minus 2 equals 0. So I moved everything to the right. So x squared became positive. 3 minus 2 was 1. -4 plus 2 was -2. So if it would help, I can write those in here. I subtracted 2x, I added x, and I added 2. And so I subtracted 2x, I added 2, and I added a positive x squared, sorry. All right, so now we have x squared plus x minus 2. We're going to factor that, and that's going to give us x plus 2 and x minus 1 is equal to 0. And that means x equals -2 and x equals +1. So checking this out on our calculator, I'm going to have absolute value of x squared minus 2x plus 2. And then as my second equation, I'm going to have 3x minus 4. Now, I find it easiest just to graph the two separately, a little bit less algebra involved, and then finding my intersection points. Now, when I graph this here, I know you might be a little thrown off seeing the parabola, but if you look at the equation, we've got x squared minus 2x plus 2. That graph is opening up and it starts above the x-axis, so it's just going to look like a parabola. There was nothing to flip up from the negatives because none of that graph was in the negatives. And then we also have 3x plus 4. Now, if we look at this, it almost looks like we have a tangent line here where they're just touching at one point, but it's really important that you check a little bit closer. And so a trick that I use is under zoom, I use zoom box. So I'm going to choose zoom box. It's almost kind of like an etch-a-sketch. You got this little cursor that you got to arrow left and right. And I'm going to use that to create a box around where I see those intersection points. And the reason I'm doing that is because I want to make sure that there's not more than one there. Depending on how zoomed in or out it is, it might look like one intersection when there's actually more than one. And so if we look closely here, we can actually see that there's two intersection points, one right here, one right here. It's just that they're so close together that we didn't see them before. So I'm going to go second calc 5 for intersect, enter, enter, enter. And one of my intersection points is happening at 3. And then I'm going to arrow down to do this one here. So second calc 5, I'm going to arrow down so I'm closer to that other intersection point. Enter, enter, enter. And my other intersection is happening at 2, 2. So doing a quick sketch again here. I have a graph that looks like this. I have 2 points of intersection. So I have one up here and one up here. And this one here, it happened at 3, 5. And this point here happened at 2, 2. So that means x is 3 and x is 2. So looking at this here, this is a solution. X equals 2 is a solution. X equals -2 is not a solution, and neither is x equals 1. So these are extraneous. So again, checking graphically, whether you choose to check by using left side, right side, or whether you choose to check graphically, you need to check all of your answers. All right, so one final example here, we're going to be looking at a word problem. So we're told that a car is traveling towards the Saskatchewan-Alberta border. The car is 150 kilometers from the border and is traveling at an average speed of 100 kilometers per hour. And we're asked to write an absolute value equation to represent the distance of the car from the border after t hours. And again, we're told that velocity equals distance over time. So our distance would be our velocity times our time. So if we want to write an equation here, we know that we're at 150 kilometers. It might even help to have a visual of this. We're starting at 150 kilometers from the border, and we're getting closer and closer and closer and closer and closer to the border, and eventually we're going to go past that border. But because we're dealing with absolute values, we're still talking about the distance from the border. So essentially, this part here flips up when we take the absolute value. So this is going to be a negative slope, and we start at 150. And since we're traveling at 100 kilometers per hour, the distance between that border is changing at a rate of 100 kilometers per hour. So our formula would be the absolute value of 150 minus 100t. Now, some of you might be thinking about it in terms of y equals mx plus b. So you might be thinking, well, my slope is negative 100 because the distance is decreasing. So negative 100 times the time plus the 150 that we originally started from. Okay, I've just written it a different way here. Now that's our expression or our equation. We then want to go through and solve the next question. So we're asked to determine when the car is 25 kilometers from the border. So we don't know if that's before or after the border. We're just looking at 25 kilometers from the border. So that will happen before we hit the border and after we've moved past the border. So setting up our equation, we would have the absolute value of 150 minus 100t is equal to 25. So considering our two cases, case number 1, we're looking at the positive. So we have 150 minus 100t is equal to 25. And case number 2, we're looking at the negative. So we would have negative bracket 150 minus 100t is equal to 25. So solving the first case here, we have 150 minus 100t. So we're going to move the 150, negative 150, negative 150. And that's going to give us negative 100t is equal to negative 125. And if we divide by negative 100 on both sides, we're going to have t is equal to 1.25 hours. Now for the next case here, we have negative 150 plus 100t equals 25. We would add 150 to both sides, and that gives us 100t equals 175. Dividing by 100 on both sides, we're going to have t equals 1.75 hours. Now we can again check these or verify these graphically or by using our left side, right side, but in this case, both solutions work. So at 1.25 hours, we're probably 25 kilometers before the border, and at 1.75 hours, we've now crossed the border and we're 25 kilometers on the other side of the border. All right, guys, so that's all the examples I have for you today. Just remember that you always have to check both cases and you always have to check for your extraneous roots. Have a great day and we'll see you soon.